So this is the memo for tutorial test 1, which was actually pretty poorly done. And I suspect, even though I did warn you as a class that it was going to cover all my work, I think a lot of you just focused on some of the Grignard reactions I noticed during the tutorial, which was a bit of a pity. So this first question is just really basic, fundamental core understanding of functional groups and things like that. So you've got a whole list of different molecules over here. It looks quite complicated. I do give, it's actually marked 2 marks each, actually is a lot of marks for a question like this. But nevertheless, you should be able to identify these things fairly quickly. So the first one talks about morphine. It's has an ether phenol functional groups quaternary chiral center. So you have a look at the different molecules over here. The fact that it's got a phenol and an ether, the only phenols that are around are this. That's not over there. So those two over there look a lot. They've got phenols, they've got ethers. So there's a quaternary chiral center. Yep, there's a quaternary chiral center and an isolated double bond. So that's the only thing that's different. If you notice between those two things, that's conjugated. So the answer there must be A. Next one talks about lysergic acid. LSD is a dangerous psychedelic. It's used and it has a chiral center and 4 cyclic rings. So this one actually you had to think about. Look at the question over here. It says it's diethyl amide. So it has a chiral center and 4 cyclic rings. Actually applies to these 2 molecules over here. And what's the difference? Well, that functional group is an amide, that functional group is an amine, and it's a diethyl amide. So it must have been answer I. Then mescaline is a psychedelic alkaloid, blah blah blah, that's all unimportant. It has a primary amine and an aromatic ring with 3 methoxy groups. Okay, 3 methoxy, possibility, 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 but it's an aromatic ring, so this one is not anymore. So it has to be either those 2 things, but it says it's a primary amine. That's a primary amine. This one over here is a secondary amine, so it must be K. The next one spoke about trifluoromethylpiperazine is not used medicinally, but occasionally misused as a recreational drug. It's a meta-substituted aromatic ring. So the key thing here is this trifluoro. So we are looking for this or this. This is a distractor. It also happens to be a meta substituted ring, but it's no fluorines over there, and this one is para substituted, this one is meta substituted, trifluoro, so it must be that answer over there, so which is J. Isobutanitrite is misused as an inhalant recreational drug. It's isobutyl. Now when you look at this, I gave you the molecular formula there. It's only these 2 as options. This one is iso, this one is a sec-butyl nitrite, so the answer must be B. Okay, so that was a fairly, should have been an easy question. This one over here, typical testing, understanding whether things are aromatic. Yes, this is aromatic. Why? Because it follows Huckel's rule. So Huckel's rule. And why does it follow Huckel's rule? Because it is cyclic, it is planar, and it has 4n plus 2 pi electrons. All right, we've got 1, 2 there, 1, 2 there, plus the lone pair of electrons that's on the sulfur is able to delocalize into the system. That's one of the examples that I spoke about in class. I just use nitrogen, not the sulfur version, but it's exactly the same thing. So therefore it is aromatic. This question over here is a very typical HOMO-LUMO diagram that we've spoken about. We have to do the reaction using cyanide with benzaldehyde. I've already given benzaldehyde to you over here. So we've got cyanide is adding to benzaldehyde as the nucleophile, benzaldehyde is the electrophile. We were using therefore the pi star orbitals. So the pi star orbitals look like this. And they have to be shaded in. All right, they've got to be opposite phases like this. We identify this as the pi star antibonding. get our full marks. And the nucleophile coming in is the nitrile, and it's important just to remember that the nitrile is a linear molecule, so we need to just make sure that we're drawing it in. There's now the lone pair of electrons sitting, okay, in this orbital over there, and the interaction that's occurring like this is the trajectory is coming in quite nicely like that. In fact, that trajectory is 107.5 degrees, also the Bürgi-Dunitz angle. This would have been for bonus mark, all right? That's an extra mark. It would have been 5. It's 5 out of 4. This orbital over here is lone pair, or better is a non-bonding orbital. Okay, it's not a sigma star or a sigma or something like that. It's just a lone pair non-bonding orbital. This one over here is our HOMO, and this one over here is the LUMO. All right, and that would have been enough to have got you your 4 marks, well, 5 marks if you put this over there. All right. Then here's this typical question again. What is the strongest base? What are we looking at? We've got a carbon, nitrogen, oxygen, and oxygen over there. Well, carbon always wins, so it'll be the strongest. Nitrogen is always less strong than carbon, but stronger than oxygen. Got 2 oxygens. This one over here, no resonance stabilization. This one over here, the negative charge can resonate into the aromatic ring, so it's stabilized. So this one must be the strongest. This must be the weakest of the 2. Then we have to formulate the different reagents and starting materials and products for this one over here. This is your, looking at this, this is your Grignard type reaction. To get something like this would be a typical way of doing it. In fact, there's a lot of different answers that you could have given over here. But it just depends on which side you cut it on. So the one might have been something that looked like this. And then you got the magnesium bromide. Okay, notice how I drew that. The magnesium was bonded to the carbon over there in the sigma bond. So that would have, and if I did that, then the aldehyde part would have looked like that over there. Okay, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, and 5 for that methyl group. But I could have also done a Grignard reaction if I'd cut it this way over here as well. So then it would have been this magnesium bromide. And the aldehyde would have been this one over here. So it's that aldehyde. All right. So, and there's yeah, number of options there. Okay. So this is an oxidation, and so PCC is one that would have worked over there. Also Jones's reagent would have also worked, which is chromium, the chromates, chromium oxide. All right, this over here is, we recognize a nucleophile and an alkyne. There's an electrophile with an aldehyde over there, and we're just finishing it off. In fact, this was a question which was in a problem set that we did in our research group fairly recently. So this is a real-world type example, and 1, 2, 3, we've connected that carbon to that oxygen, which is there, and we fill in the rest OMe like that. All right, and then from there to there, this is an important transformation to be able to recognize. We form a new carbon-carbon bond. There we've got a carbon-halogen bond. What do we do? Need to make that nucleophilic. One option is to add magnesium, so that we make the Grignard reagent, which we then need to trap with CO2. And lastly, we need to add some mild acid, H3O+, to quench it to get the carboxylic acid. This step over here, this first step though, you didn't have to just use magnesium. You could have used lithium, or you could have done a lithium halogen exchange with butyl lithium. So there are actually a number of options that you have in order to make this carbon nucleophilic to react with carbon dioxide, such that we end up with this carboxylic acid over there. Okay, so this was a theory type question. The following three carbonyl compounds undergo a Grignard reaction with phenyl magnesium bromide, but at different rates. Rank the compounds from most reactive to least reactive and give an explanation as why you chose this ranking. The explanation should be more detailed than one word answer. So I think a lot of people got the ranking correct. The aldehyde is always the most reactive. Ketones are less reactive. Compare these two ketones over here. This one is more sterically hindered because it's got this isopropyl group there versus a methyl group over there. So 1, 2, and 3. So I've already given the answer. The answer is steric hindrance. But I didn't want just one word answer like that. I wanted a bit of an explanation. Why is it steric hindrance? Well, it's as reaction occurs, the C double bond O changes from sp2 to sp3, and that is that equates to a change in the bond angle. Here it's 120 degrees. When it goes to sp3, it goes to 109 degrees. So we're going from 120 degrees to 109 degrees, or 109.5. Therefore, the groups bump into each other. All right, so something along those lines, just identifying that the basic thing is remembering steric hindrance. This is not electronics over here, this is sterics. But what does that actually mean? I need to know that you can't just say steric hindrance, because again, it could be, remember, there's two options, steric hindrance or electronics, and that's a 50-50 chance. I need to see that you understand what you mean by writing steric hindrance in a question like this. All right, so then here we've got amines are excellent nucleophiles in many reactions, which amine is a better nucleophile. I'll give a reasoning. The better nucleophile is, this is to do with resonance, but the better nucleophile is this one over here. This one is better because the lone pair of electrons, remember the lone pair of electrons is the nucleophile. It's the part that's going to add. This one, the lone pair, it can't go anywhere. All it can do is sit on nitrogen. Whereas in aniline, it can be stabilized by resonance. Because in aniline can be stabilized through resonance. Therefore, not as available. And then you can show that. What do you mean by resonance? NH2, lone pair of electrons kicks in and we kick out. And just show one example of that so that it's not H2, there's a plus on that now and a minus on this carbon there, and of course that can continue around. Okay, so if you're given something along those lines, that would have been full marks. And then lastly, use your knowledge and mechanism to predict the outcome of this reaction over here. This is, again, it's really important to be able to predict mechanisms of things that you would not have necessarily seen up until this point. By now, I think you have seen this, the formation of an imine. You have certainly seen it in first year, but maybe not the mechanism. But here, it's applying the rules. What you should recognize is that effectively this nitrogen has connected with this carbon over there. And nitrogen is a lone pair of electrons, which is nucleophilic. Carbonyls are electrophilic, and so they should be able to pick it up. That's what I would expect is the interpretation, it's the prediction ability. We don't want to teach you to learn things off by heart. Rather, you should be able to look at something and say, oh, hang on a second, I know the rules. We've got some acid present over here. What are the rules? The first thing is we normally protonate a carbonyl to activate it. That's the basic sort of principle that comes into play. So once we protonate the carbonyl, we've now activated it, so the lone pair of electrons can now add there, and we can kick out All right, in this equilibrium. So we've now made a 5-membered ring. The nitrogen has 2 hydrogens on it still, so it's positively charged. There's the carbon that went in over there, and it's got an OH on it over there. So what we still need to get to the double bond. So what needs to happen? Well, the water needs to leave. So we need to protonate that. We've still got an acid present, and we also need to get rid of one of these H's because the product doesn't have any H's on the nitrogen. So that's okay. The proton can leave like that over there, and we can get another proton from, I mean, that one's left. It could be the one that goes onto there, but not directly. We get another proton from the media, and we typically talk about this being a proton transfer step. And so now we've made the OH into a good leaving group. It's water, OH2, so it's plus. So it's going to leave, but the lone pair of electrons of nitrogen can kick in like that to cause that to leave. And that gives us the double bond over there. And in fact, we're now basically finished with this because we just need to get rid of a proton because this one is now positively charged, and that's easy. We can just go like that, and then that's our product because the proton leaves. So overall, this was catalyzed by that. We added one proton over there. We added another proton over there, but we took off one proton over there, and we took off another proton over there. Okay, so that was the answer the memo for tutorial.